Assalamu alaikum everyone. First of all, I would request you to log in to your respective workstations and open your Colab. एक प्रिंट मुझे भी दे दें, प्रिंट आउट मुझे भी. All right. So the purpose of today's session is very simple. What we're going to do is we're going to do an exercise and we're going to do it together. The idea of this hands-on exercise is to take a deeper look into data. What is meant by uncertainties? How do we plot data? How do we linearize? And so on. So data has many facets. It has many sides to the same coin, and data needs to be processed. So whenever you do an experiment or you do a measurement, you get data. Now, drawing inferences from that data is important. What does that data mean? Every data speaks a language, and that language is statistical, mathematical, computational. So today we're going to look at some data, very simple data, and try to draw an inference from it. We're trying to do a measurement. All right, so that's the purpose for today's expository session. So first of all, each one of you has received a piece of paper, two leaves, and this is an experiment that we've already performed. So the experiment was very simple. It really looked at a very simple circuit. So has everyone logged in? आपने login नहीं किया? So the circuit was very simple. So we had a capacitor and a resistor, and to this circuit we connected a phase logger which produced a sinusoidal voltage. Correct? So there was an input. The input was a sinusoidal wave of amplitude, say 5 volt. This was our V naught. Okay, and a certain frequency, F. And what we did was we varied the frequency F, very simple, and we looked at the voltage generated across the resistor. We call this VR. Okay, and there was an output. The output voltage had an amplitude smaller than V naught, smaller than 5 volts, some voltage. We call this voltage, this amplitude, VR. Okay, so we varied the frequency and we measure VR. All right, so that was our experiment, very simple, and we acquired data. So the data is given on page number 2 of this pair of leaves. So on the table you can see a listing of frequencies. You vary the frequency and you measure VR. Right? So everyone is with me on this? You measure VR. VR is of course smaller than 5 volts, and as you change the frequency, VR changes. Now if you want to go deeper into this circuit, into this hardware, you can explain what's happening here. This is an AC voltage. This capacitor has an impedance. The resistor has a certain resistance, and the impedance of this capacitor changes as the frequency changes. So you can go into the physics of this, but that's not the point today. Okay? So we can discuss offline what's happening here. How does the current flow through the capacitor even though there is air in between the plates of the capacitor and so on. That's the physics of the problem. But we're not going to talk about the physics. The purpose today is to expose to you that once we have data, we have frequencies and we have measurement of VR, can we infer something about the circuit? And the kind of decision that we would like to make is that we want to find out this resistance R. This resistance is unknown. We don't know this resistance. But we do know that there's a capacitor here, C, whose capacitance is given. Okay? The capacitance is, in our case, 0.1 microfarads. Okay? So given this data, we would like to make an estimate of the resistance. This is a measurement, this is a course on measurement, so we would like to make a measurement of the resistance. And measurement always means we would like to make an informed guess, an informed estimate. And since you're scientists and engineers in the making, by an informed estimate you mean you would like to find out the best estimate for R. And what's the uncertainty around it? Okay? So your R could lie between in this range with a certain confidence. That's what you want to do. Now the only thing that you have in front of yourselves is the data. Someone else may have performed the experiment, you may have performed the experiment, but once you get the data, a new world of opportunities open in front of you. So now we would like to analyze the data. So the first thing I would like you to do is, I would like you to now focus a little bit on what we have in front of you, and probably this is something you should be able to do on your own. First of all, can open your new notebook and initialize, import some libraries so that you can start processing the data. Okay, import these libraries here and input your data into two arrays, one for the frequency and one for VR. ठीक है, अब आप थोड़ा सा इनको, ठीक है, अब ये साथ साथ करेंगे हम ये काम. Make two arrays, one for the frequency and one for the voltage across the resistance. आप नहीं कर रहे? कर चुके? देखो ये प्रैक्टिस आपको अब तक हो जानी चाहिए अब, लेकिन चलो करो. ठीक है, आगे चलें. So does everyone have an array for the frequency and an array for the voltages? Each array must be of the same size, same length. Now can you make a plot between, so the first thing that you would like to do, whatever the scenario is, you would like to find relationships between variables. Now one variable is frequency and the other is voltage across resistor. Question, well, which variable do you think is the independent variable? Frequency, because you control it. It's within your desire to control the frequency and you measure the voltage. So you want to plot the frequency on the x-axis and the voltage on the y-axis. So make a plot please. और देखते हैं किस तरह का आप प्लॉट बनाते हैं. ठीक है, label your axes. The plots, ठीक है, plots में खाली data points होंगे, only the data points, no line, because the line represents a model. You do not have a model as yet, just the data. Remove that line and write. Remove the line, just data points. Line remove karo, sirf data points. So once you have the data, so your experiment is digital, discrete. You'd never have a line in an experiment. The line represents some model. Here you do not have a model as yet. You just have data, so you draw discrete points. So this is what your data may look like. The frequency here, there is a voltage across the resistor measured in volts and just raw data points. Nothing more, nothing less. No line, no artificial line, because still you do not have a model. Now, is this a linear relationship? Do you think there is a linear relationship between frequency and voltage? No, because if this was only, so there is, it doesn't look like a linear relationship. So now, in order to develop an idea of how you measure the resistance, what you would like to do is you would like to develop a model. Once you have data, you would like to look for a model. What is a model? A model is a mathematical description of how this data can be explained. That's a model. Ohm's law is a model. Newton's law is a model. Gravitation laws are models. Ampere's law, Faraday's laws, all of these are like models. So now like to look or search or invent a model that describes this data. Okay? So in the handout that has been provided, there is already a model given to you. That's equation number 1. Okay, so in the handout, first page, equation number 1 represents a model. क्या हो गया भाई? प्लॉट से ऊपर वाला हाँ आप करो, इसको फॉलो कर लें अगर किसी से अभी तक नहीं हुआ. In front of you, we have proposed a model to you. Okay, so that model is given by equation number 1 in this handout. Now as scientists, in most cases you would like to invent your own model or search for your own model that describes the data. Okay? But in this case, we've given you the model. Now this model has, let me write down the model on the blackboard. The model is that VR equals V naught into R, which is unknown, divided by square root of R square plus 1 over 2 pi f c whole squared, and all of this is within an under root. Okay, so this is our model. Okay, this relates VR to frequency, but it's kind of all jumbled up, it's highly non-linear. And we expect that the data that you plotted is somehow related to this model. So we want to see what kind of predictions does this model give, and does the data match the model, or can the data be explained by the model that we proposed? That's what we would like to do. Okay, so in experiments, in experimental natural science, you come up with data, you invent a model or take out a model out of the closet and see if your data and the model match. You do a matchmaking. All right, every time you do this. So now it's this first question. Is VR a linear function of frequency? No, it's not. That's one thing. The second thing is, you may or may not know how is this model derived. For the enthusiast, I would just like to mention that this is just a voltage divider. So there is some voltage here, some of the voltage appears across this capacitor and some across this resistor. But the capacitor behaves differently from a resistor. Its impedance, as it is called, depends upon frequency. For a resistor, in most cases, the resistance does not depend upon the frequency, in most cases. Okay, so this is how this equation is derived. But you need not be concerned with the derivation of this equation. But the model is in front of you, and we would like to see whether the model and the data match. And in the process, can we infer or estimate the value of R? That's the question at hand. Right? So in this laboratory, all of the experiments, all of the work that you've been trying to kind of share with you is around this central theme. So what now happens is that this is a non-linear equation, and what we would like to do is we would like to linearize this model. Can we manipulate this equation, this model, such that we have a variable which two variables, say one is y, one is x, and there is a linear relationship between y and x. So this is something you'll have to do on paper. So the next assignment I would like to give to you is, now we can forget about the hardware. Okay, so we have done the experiment, we have a proposed model. I would like you to kind of recast this equation. Recast means mold this equation, change the order, change the numerator to a denominator, do something so that this equation is linearized, which means I would like to write this expression as y equals m, which is a slope of a line, plus c. So if I have x here and I have y here, I can draw a line which is a straight line which has a slope m and an intercept c. So this is a linear model, correct? So I would like to massage this equation, change this equation so that I have a form for this model which is linear. So I will give you 5 minutes to kind of do this on paper. So I have two variables, y and x. Here I have two variables, vr and f. So I would need to kind of come up with new variables which somehow depend upon vr and f, in which there is a linear relationship between those inferred variables. So kind of try to rewrite this equation number 1 in terms of a linear form on paper. One over VR square equals 1 over V naught squared plus 1 over F squared and one over 4 pi V naught squared C squared R squared. So this is our relationship. This is the same model, nothing new with this model. This equation is exactly identical to this model, only that it has been written in a different form, in a linear form. All right? So you've changed the subject of your equation and manipulated everything so that this same equation is written like this. Now this equation is cunningly similar or identical to the equation of a straight line, in which y, which is a dependent variable, is 1 over Vr square. So Vr was your dependent variable, now 1 over Vr square is your dependent variable. X is 1 over F square. You have F square, you have 1 over F square. This intercept is 1 over V naught squared. And the slope of this line is this collection of parameters, 4 pi V naught squared, C squared and R squared. You know all of them besides R. So if somehow your data, when recast in the language of y and x instead of Vr and F. So instead of Vr and F, you work with y and x, which are defined in this fashion. And see if your data now, if you make a plot between y and x, y is 1 over Vr squared and x is 1 over F squared. So what we would like to do now is we would like to make a plot between y and x. So first of all, define your y, define your x and make a plot between y and x and see if you get the semblance of a straight line. Okay? Let's see if we get something like that looks like a straight line. This act is called linearization. We're trying to linearize the model. So please make a plot between y and x, where y and x are defined in this fashion. Different ways of achieving the same thing. You might use your own way, but how I have done this is y is 1 over a square for a in Vr This is how I have done it. You need not follow this approach. You can do whatever you like. For each A in VR, which is an element in the voltage, I take 1 over A square, and my X is 1 over A square for A and F. So this is how I define Y and X. This is how I have done it. You can do it in another way. So I want element by element squaring and reciprocal. दो तीन मिनट और ले लें फिर हम आगे चलते हैं. Recasting of variables. This axis is now my x axis. This is 1 over f squared. This axis is 1 over VR squared. And I get this scatter of points. Alright? Now all of these points look roughly along a straight line. This point looks a bit wayward. The point at the top looks a bit wayward, but so far we haven't taken into account any uncertainties. We'll look at these uncertainties later. ठीक है? अच्छा मुझे फॉलो करो. देखो इधर. अब हमें क्या करना है? What should our next steps be? Any ideas? We want to find out the resistance. First of all, there are two things we would like to do. First of all, जी. इसको कॉपी कर लो अगर, क्योंकि इसके बाद हमने आगे चलना है. और इसका 1 over VR squared है. ठीक है, तो स्टिल रेसिप्रोकल ऑफ स्क्वेयर्ड. ठीक है, चलें. What should be our next steps? What should we do next? Speak up. क्या करना चाहिए? किस चीज का ग्रेडियंट? अभी लाइन तो बनाई नहीं, पहले तो लाइन बनाएंगे. First of all, we would like to draw a best fit line and see if that line negotiates most of these points. That can tell whether the data is describable by the model that we've proposed. All right? So that is matching the data with the model. So we draw a best fit line, and there are algorithms to do that. You know what the best fit line? The best fit line has the minimum of the sum of the squares of the distances between the line and the points. Right? This is how we define the best fit line. But you don't need to remember this because there are algorithms in softwares that provide this optimization routine. So this is how you can do one method of doing a best fit. You take your variables x and y and you do an np.polyfit. Polyfit is a library from the numerical package, polyfit, and you do a linear fit. This one shows that you're doing a linear fit. And the output, every linear fit, finding a line means finding MNC, finding the slope and the intercept. So when the algorithm runs, it must give you the slope and the intercept. Once you have the slope and the intercept, you know the line. So this is how we define the slope and the intercept. So the output for this algorithm must give us the slope and the intercept. Now you want to plot the line with this slope and intercept. So you define your best fit line. Your best fit line is then the slope that you just obtained multiplied with the points that you have along x plus the intercept. And then you would like to plot your data, the original data that you have after this variable refashioning and the best fit line together on the same graph. So you can see whether your data is in consonance with the model. Your data matches the model. That's what you want to do. जितने भी आप काम करोगे इस लैब में या लैब का बहुत सा वक्त गुजर गया उसमें यही प्रोसेस फॉलो होना है. ठीक है? So kind of try to find the best fit line and plot the best fit line and the data all together in the same graph. Done it? Very nice. Good. Good. So far we haven't taken into account any uncertainties. Keep that in mind. उसको याद रखना. साथ साथ इसकी डिस्कशन भी करते रहे ना. So now these are the data points and this is the best fit line which gives equal weightage to all the data points. ठीक है? Because we haven't yet taken into account any uncertainties. Each point may have different uncertainty but we haven't yet taken that into account. So according to the algorithm, this red line is the best fit line which comes from the model. The red line represents the model. The blue points represent the data. And you can tell it's a good, the data is well represented by the model. Now in order to find this unknown parameter r, you need to know the slope. But the algorithm has already given you the slope. Can you please now from the slope find out your estimate for the resistance R? आपके पास वेरिएबल्स भी हैं, स्लोप और इंटरसेप्ट आपके वर्कस्पेस में वेरिएबल्स मौजूद हैं. हाँ, आप R की वैल्यू प्रिंट करके बताओ. हर्ट्ज स्क्वायर पर वोल्ट स्क्वायर इसके यूनिट्स होंगे. तो उस स्लोप से आई वुड लाइक यू टू फाइंड आउट योर एस्टिमेट फॉर आर. जीरो टू क्या
कैपेसिटर की वैल्यू 0.1 माइक्रो फैराड यूज की है जी. 0.1 माइक्रो फैराड.
माइक्रो क्या होता है?
10 raised to power -6
-6 होता है.
8.377 वैल्यू गलत है.
हाँ नहीं ये नहीं है. 1000 ये ठीक है. 16,000 ओम, 16 किलो ओम. रफली योर आंसर, आपका क्या आ रहा है आंसर? Something 16,000 ohms. Okay, 16 kilo ohms. All right. So let's see. All right. So this is what you should get. 16,000 ohms. 16 kilo ohms roughly. All right. Now the point is we still, okay, idhar tawajjuh do, this is something really important, and this is kind of twist to the story today, the twist to the plot. As metrologists are people who measure things. Idhar suno baat, bhai, idhar baat rakho. You want to measure something, so you want to be perfectionists. So you need some confidence in this resistance. But without uncertainties, you cannot assign any confidence, any level of confidence to this value of the resistance that you're estimated. So, by the way, every experiment gives you an estimate with some confidence. In order to properly gauge the validity or the confidence that you have in this result, you need uncertainties. Okay? So let's come to the uncertainties. If you look at your data, this is our plot. By eyeballing, by inspection, you can see that this point over here, which is at small values of frequencies, because this is 1 over f squared on the x-axis. So if you go to the right, f decreases. So at small frequencies, this value seems to be kind of not following, not lying. If you were to draw a straight line around these points, this value would fall below that line. So it's kind of wayward. It's kind of out of context a little bit. And when you drew this red line, you had no idea whatsoever of the uncertainties. And when you drew the best fit line, each point was given equal emphasis. Each point was given equal weightage. Now what we would like to do is we would like to assign uncertainties to these frequencies and to the voltages that we've received and see if we can improve our estimate a little bit and also improve the corroboration or the consonance or the matching between the theory and the experiment, between the model and the data. So now let's sprinkle in uncertainties into our data. ठीक है, अब बात समझ आ गई कि हम क्या करना चाह रहे हैं, philosophy समझ आ गई, what we're trying to do. We're trying to pour in uncertainties into this data and see how our estimates for R can be improved. They can be tightened a little bit, क्योंकि अभी हमें कोई पता नहीं कि uncertain कि ये 16,000 हर्ट्ज है, इसमें 70,000 भी हो सकती है, 18,000 भी हो सकती है, 12,000 भी हो सकती है. What's the range of values that we are expecting? Okay, so let's sprinkle in uncertainties into the same problem. तो कोई भी आप काम करो ना लैब के अंदर डेटा के साथ, this is the process you need to follow and it's very systematic. Very systematic. You just need to take a deep breath and think and do it carefully, slowly, once or twice in your lifetime, and you'll remember all your lives. Okay, so now let's sprinkle in uncertainties. By the way, the homework associated with this problem is, I would like to ask you a question. अभी हम करेंगे नहीं, लेकिन ये जो data आ रहा है ना, all these points are clustered in one region as a result of the linearization process. The original data, which was the raw data, looked like this, frequency and VR. But when you linearized, all these dates, lots and lots, all of these data points were clustered into one small region. So these look like evenly spaced points with the raw data. But once you linearized, you get this clustering behavior and it doesn't look nice to the eye. It looks a bit difficult to kind of analyze. So I would like to ask a question. Is there another kind of linearization that still keeps the data linearly spaced, linear and equally spaced? Is there some other mathematical function that you can use that can keep the model linear and still the data remains equally spaced? कोई और मैथमेटिकल फंक्शन है? अभी तो आपने स्क्वायर कर दिया ना डेटा को, स्क्वायर करके रेसिप्रोकल ले लिया. दैट्स अ फंक्शन दैट यू अप्लाइड ऑन योर डेटा. Is there anything else you can think of which kind of equally spaces out the data? Shabash. Log. Log is a very nice function. Now look at the numbers 10, 100, 1000, 10,000. They're not equally spaced. 10 से छोटा सा jump ले 100, फिर बड़ा jump ले 1000, फिर 10,000. The jumps keep on increasing. So the data keeps on, is uneven. 10, 100, 1000, 10. It's uneven data. But once you take the log of these numbers, you get 0, 1, 2, 3, 4. It's evenly spaced. So another way I would like you to do this as a homework is take the same data and do a linearization through a log plot. Take this equation over here, and linearize it through log mechanism. So your y becomes log of something and x becomes log of something. And see if you, by the way, I've already done this homework for you. I'm just going to flash the results. When I do a log plot, this is what the data would look like. Okay? So I would like you to come up with these two new variables, these new y and x, which kind of equally spaces this data, and then do a linear fitting and see how you get the resistance from this data. Just another cherry on the top of this cake is that the resistance from this data will not come from the slope, rather it will come from the intercept. This is something very interesting. So try to do this on your own. Now let's come back to the uncertainties. Now what I would like you to do, where do the uncertainties come from? The uncertainties come from when you're doing the experiment. So while doing the experiment, you have an estimate of what the uncertainties are. Depends upon the resolution of your instrument, depends upon how good your instruments are. It also depends upon whether you are using an analog device or a digital device, the rating of the instrument, because you're measuring voltages and frequencies. Okay, so all of this comes from the experiment, and this is a judgment call. ये कोई पत्थर पे लिखी हुई तहरीर नहीं है कि इसको बदल नहीं सकते. It's your judgment call as an experimenter. There is some subjectivity to this. Alright, so you estimate your uncertainties, and you can be conservative about it, and you can be flimsy about it, but you make your estimates. Now what I would like to kind of do is to keep things simple. Let's assume that whatever frequency you have, there is an uncertainty of 10%, and whatever voltage you get, there is an uncertainty of 10%. Right? 10% uncertainty in whatever frequency. So can you make an array of uncertainties of frequency and an array of uncertainties of voltages? 10% जो भी frequency है 50 hertz, 10% 5 hertz. 60 hertz, uncertainty is 6 hertz. So this is a good mechanism of kind of playing with uncertainties. Assign 10% uncertainties and make arrays for uncertainties in frequencies and voltage. Now, what really is happening is your variables are y and x. अच्छा, अब ये बात बड़े ध्यान से, क्योंकि you understand this, you get all of it. Your variables are y and x, correct? So you need the uncertainties in x and in y. So this is your x. So what is x in terms of frequency? What is x? 1 over f squared. What is your y? 1 over VR squared. So you know your uncertainty in f is 0.1 of f, whatever f there is. So when you know the uncertainty in f, you want to find the corresponding uncertainty in x. Correct? समझ आई? अगर किसी को नहीं समझ आई वो हाथ खड़ा कर ले, मैं उसे दोबारा किसी और लैंग्वेज में समझा दूंगा. समझ आ गई बात? कि अगर आपको x के अंदर अनसर्टेनिटी निकालनी है तो जो f के अंदर अनसर्टेनिटी होगी वो ब्लीड थ्रू होके x के अंदर अनसर्टेनिटी में नुमाया हो जाएगी. ठीक है? बिकॉज x really depends upon f. Whatever uncertainty exists in f bleeds through towards x. So, and likewise any uncertainty in VR goes into y. Now if you know the uncertainty in f, what's the corresponding uncertainty in x? It's very simple to do. I know my x equals 1 over f squared. I know this. Let's finish this equation here. My uncertainty in x will depend upon the derivative of this with respect to f and multiplied by the uncertainty in f. Alright? Are you with me on this? So your x is 1 over f squared. You find the derivative of 1 over f squared with respect to f and multiply this with the uncertainty in f. ठीक है? So what's the derivative of 1 over f squared with respect to f? Minus 2 over f cube. So forget about the minus sign. We're dealing with uncertainties. So let's take the absolute value 2 over f cube. 2 over f cube into the uncertainty in f. The uncertainty in f is 10% of the value of f. Got it? Alright? Likewise, the uncertainty in y is, now y is 1 over r squared. You differentiate this with respect to VR. You get 2 over VR cube with the minus sign. Ignore the minus sign. 2 over VR cube multiplied by the uncertainty in VR, which could be 10% of the that value of VR. So you get a table of uncertainties in x and a table of uncertainties in y, and I've done this for you. So look at this piece of code. You see here, look at this code. Ux is my array of uncertainties in x. What is my uncertainties in x? It's 2 over whatever the a is my running variable. It's some number inside my array of frequencies f. It's 2 over f cube multiplied by 0.1, which is 10% of that value of f. Okay? So this will give me the list of uncertainties in x. Got it? Likewise, uy is found by exactly the same mechanism. If I want to find out what ux's are, these are all my ux's. I can find out my uy. So can you please write this piece of this code or something similar according to your own disposition? I would like you to find out the array of uncertainties in x array of uncertainties in y. Uncertainty तो कैसे नजर आएगी एक derived variable में? x और y actually derived variables है ना, वो कोई फंक्शन है फ्रीक्वेंसी और वी आर का, ठीक है, वो सिर्फ आपके डेरिवेटिव से आएगा, डेरिवेटिव लेंगे। और ये एक्चुअली जो होशियार लोग हैं वो जानते हैं कि टेलर सीरीज से आ रहा है। एनीवे, नाउ आई वुड लाइक यू टू plot with the uncertainty bars included, so you get a feel of what's going on. So the command for that is error, plt dot error bar. So this is how you could do this. So can you kind of repeat this? So how do you get this plot? You just, instead of plt plot, you type plt error bar, your variables x, y, you define x error, which is ux, y error, which is my uy, just this styling command. Okay, this is how you do plots with error bars. And this is the plot that I obtained. Do you get here? Did you get here? Good. Nice. Good. Very nice. You'll get this plot. Now let's speak up. Let's have a conversation. What does this plot tell us? क्या? Okay, we're not robots, we're not machines, we are thinkers. Now there's a plot in front of us. What conclusions do we draw from this graph? What does this plot tell us? इससे हमें कोई आगे बढ़ने में कोई रोशनी नजर आएगी कि हम आगे कैसे बढ़ सकते हैं? देखो ना, हमसे ये बातें कर रहा है. दिस ग्राफ इज टॉकिंग टू अस. हमें क्या कह रहा है? ये क्या क्या दुख भरी कहानी सुना रहा है ये ग्राफ? व्हाट डज इट से टू अस? कुछ कह भी रहा है कि नहीं, या गूंगा है, या हम बह रहे हैं? क्या कह रहा है ये? कुछ तो कह रहा है भाई, कुछ तो कह रहा है. चीख चीख के कह रहा है. क्या कह रहा है? किसकी अनसर्टेनिटी ज्यादा है? सब पॉइंट्स की एक जैसी अनसर्टेनिटी है. ज्यादा होती है. यानी कुछ पॉइंट्स हैं, फॉर एग्जाम्पल दिस पॉइंट ओवर हियर which corresponds to a large value of x, which is really a small frequency. The uncertainty in both of these dimensions is really, really large. It outweighs the uncertainties that we see over here. This is intermediate. So as we go to lower frequencies, the uncertainties are amplified, which means the points, these points, especially this point and this point, they are very noisy, very noisy. They are highly uncertain. What does this say to us? अच्छा ठीक है, हमें पता चल गया. आगे आगे व्हाट्स द नेक्स्ट स्टेप? इससे हमें अपने एनालिसिस में क्या हमें राह नजर आती है? Is there any new thing that this reveals to us? Any way forward for us? तो जो ज़्यादा नॉइजी पॉइंट है उसको उतनी अहमियत दें जितना कम नॉइजी पॉइंट है, राइट? सो द पॉइंट दैट इज मोर अनसर्टन must have less emphasis. The point which is noisier should have a little emphasis, little contribution to the resistance that we are trying to estimate. We're trying to estimate the resistance from the slope of the line. Previously, our line was made by taking into account all points with equal weightage, equal emphasis. हमने ये नहीं कहा था कि यार इस पॉइंट्स लाइन इस डेटा में से ज़्यादा गुजरे, हम कह रहे थे कि लाइन सारे पॉइंट्स को खुश रखे. इट शुड बी द बेस्ट फिट लाइन विद रिस्पेक्ट टू ऑल पॉइंट्स, इक्वल वेटेज, राइट? नाउ वी वुड लाइक टू सी, is there a way of drawing a best fit line such that we give more importance to the points which have smaller uncertainties in this collection of points? All right, that's what we would like to do. Got it? अच्छा जमाल, इनको इधर आने दो अब, क्योंकि फिर ये भी रह जाएगा. ठीक है, तो अब ये पॉइंट्स हमारे पास. अब what we would like to do, we would like to do a fitting which is slightly a twist to the original fit that we've done. We would like to do a weighted fit. Weighted fit. Weighted fit. Weighted fit gives more weightage to the points with smaller uncertainties. Okay? In order to do a weighted fit, the first thing that we need to do is we would like to make a graph that does not have an uncertainty along the x-axis. Okay, we would like to make a graph that has uncertainty only along the y-axis. For that purpose, we want to transfer the uncertainties along the x-axis to the y-axis. Okay? How do we do that? We've already done an unweighted fit. We've already done an unweighted fit. We have the slope of the unweighted fit, which was your 357. Correct? So let me show this on the blackboard. Can you turn on the lights for a minute? So now what we have is some uncertainty along y and some uncertainty along x, right? Like this. Correct? True? And we already have an unweighted fit. We've already done an unweighted fit. And we know the slope of this, m. We already know the slope of this for the unweighted fit. Now what we would like to do is we would like to transfer the uncertainties which exist along the x-axis to the y-axis. And the best way to do that is to take the uncertainty, each uncertainty along the x-axis, and multiply it with the slope. That will give the uncertainty along the y-axis. Correct? That's what the slope is meant. The slope is meant, you multiply something delta along x with the slope, you get delta along the y. That's what the slope really is. So you take all the uncertainties along x's, ux's, each one of them, and multiply it with m. You get the uncertainty, let's call this trans. The uncertainty that has been transferred from the x-axis and now exists in the y-axis. Okay, got it? But even if you did not do the transfer, there was already some inherent uncertainty along the y-axis. There was already there some uncertainty along the y-axis to begin with. पहले भी थी ना ये वाली. तो अब y के along uncertainty के दो हिस्से हो गए, एक इंट्रिंसिक जो पहले से मौजूद थी और एक जो ट्रांसफर होके आई है. Right? So now the total uncertainty along the y-axis is a combination of the intrinsic uncertainty along the y-axis plus something that has come from the x-axis, the transferred uncertainty. So this means that the total uncertainty along the y-axis is now the uncertainty that already existed along y. I'm going to improve this, plus the uncertainty that comes from the transfer. But you can't add uncertainties like this, because uncertainties can be positive or negative. What you really want to do is you take the square of this, add and take the square root. This will give you the total uncertainty along y-axis and nothing along the x-axis, but you've taken that into account already. So as a result of this transferal process, x, y, your points, you will just be left with a total uncertainty along y and nothing along x. Correct? These uncertainties, of course, will be bigger than the original because you've imported some uncertainties from the x. Okay? So now we would like to do this transferal process. And I'm just going to show you the code for this. It's very simple. Everything is so simple, by the way. Is the lights off? Cut? Now look at this piece of code. I take my uncertainty along x here and multiply it with the slope. I get the u transferred. Got it? Simple. This is the first step over here. Then I take this u transferred, I square it, I take the original uy, square it, add, take the square root, I get the u total. तो ये जो मैंने अभी इतनी तकरीर की है लंबी, computationally just 2 lines of code. ठीक है? Now I would like to make a plot with error bars, and there's no error along x. There's only error uncertainty along y, which is this u total. So let me make that plot. Here you go. Nice. The same graph, the same points, but the uncertainty in x has been shifted to the y-axis. The burden of responsibility is now shouldered by the y-axis. x-axis को हमने कह दिया यार तुम्हारे पे कोई इल्ज़ाम नहीं है, तुम ठीक हो, सारी अनसर्टेनिटी y-axis पे है. ठीक है? क्योंकि वेटेड फिट में हमें सिर्फ y-axis के लॉन्ग अनसर्टेनिटीज चाहिए. You get this? Fine? I give you 2-3 minutes to let this sink in. It is clear from this graph, it's absolutely crystal clear that you would like to give less emphasis to this point and more emphasis to these points over here because they have smaller uncertainties along the y-axis. This point really could be anywhere. With 60 to 70% probability, this point could have lied anywhere in this region, right? So you want to give less emphasis to this. So our fitting should take into account this selective judgment, this selective process, this selection of points, which means we give more weightage to the points with smaller uncertainty. All right. So higher the uncertainty, smaller the weight, right? Higher the uncertainty, smaller the weight. So now we would like to define an array for weights. Weights का मतलब वजन. We have an array for the uncertainties, U total. Now the weights will just be the reciprocal of these uncertainties. So higher the uncertainty, less the weight. So we define a new array. You see, we define this array, weights, is 1 over the uncertainty. Higher the uncertainty, smaller the weight. Actually, it should be the square of the uncertainty, but the Python library automatically takes the square, so we don't need to put the square in when we're using a Python library. So once we have the total uncertainties, we can easily find out what weights do we assign. And it's important to do a weighted fit here because all points do not have the same uncertainty. 1 or 2 points have an uncertainty which is wildly bigger than all the rest. ऐसे ही है ना? तो अब हम इस fitting करते हैं with this weight, with this series of weights assigned to the points. So exactly the same command applies for weighted fits. Exactly the same command, polyfit. X, Y, 1. This is what you've used previously, right? Up till here. This is what you've used. Now I'm adding another parameter. I would like to have a W. W is the parameter for weights. And which weights do I want to use? I choose the weights that I've defined already. If this parameter is missing, it does an unweighted fit. Or if this parameter has an array with equal values in each entry, it does not do a weighted fit. So once I do this algorithm is just used for weighted fits, and I get a slope and an intercept, which I have now labeled slope 3 and intercept 3, because the slope is now going to be different. Slope अब different होगी ना, slope कम होगी ज़्यादा हो जाएगी. So previously, so looking at this graph, ये स्लोप अब ज़्यादा हो जाएगी. पहले स्लोप कम थी क्योंकि इस पॉइंट को इंपॉर्टेंस मिल रही थी. अब इस पॉइंट को इंपॉर्टेंस नहीं मिलेगी, इन पॉइंट्स को ज़्यादा इंपॉर्टेंस मिलेगी, तो स्लोप थोड़ी ज़्यादा हो जाएगी. स्लोप थोड़ी ज़्यादा हो जाएगी, रेजिस्टेंस की एस्टिमेट भी ज़रा कम हो जाएगा. ठीक है. So let's do this weighted fit. So here is the best fit line with inclusion of a weighted array, and then I draw everything with error bars. X, Y, there's no error along X. there is some error along y, which is u total. So here is the experimental data. I just draw points for the experimental data. But for the model, I draw a line. And that line is my best fit line. Now this is a weighted best fit line. If I were to draw this, run this cell, this is what my best fit line looks like. Khoobsurat. Now the best fit line kind of averts or evades that last point. अभी भी इसको कुछ ना कुछ तवज्जो ज़रूर देता है क्योंकि इसकी अनसर्टेनिटी इन्फिनिटी नहीं है, लेकिन बहुत कम तवज्जो देता है. It gives more emphasis, and there's a formula for finding this slope, which is present on the formula sheets on our website. I'll show you that formula sheet as well. But the algorithm now returns a weighted best fit line, and as you can see, it gives more emphasis to the points, to these points here at higher frequency. And this slope is now different from the slope from the unweighted fit. Let's see what this slope is. So this is your slope. It's gone up. Previously it was about 360 something. Now the slope has gone up. And from this slope, if you were to determine the resistance, the same formula, but instead of using the old slope, I now use a new slope. The resistance is now 14.8 kilo ohms. My estimate for the resistance is now different. All right. The last thing that you would need to do, by the way, when this circuit was constructed and provided to you, the resistor that was provided in this circuit nominally means as far as the color bands on that resistor tell, it was about 15 kilo ohm resistor, right? So that was the nominal value. Nominal value जो उसके color bands बता रहे हैं, but we really don't know how precise it were. But sorry, it was 15 kilo ohm. So this one, right? 15 and all right. So this was our estimate. This is our best estimate for the resistor. However, we need to know the uncertainty in this resistance value. The question, ये uncertainty in resistance कैसे निकाल सकते हैं अब हम? Resistance कहाँ से आई है? Slope से. Uncertainty in resistance कहाँ से आएगी? Uncertainty in slope से. राइट तो अनसर्टेनिटी इन स्लोप हमें चाहिए. अनसर्टेनिटी इन स्लोप का मतलब ये होता है कि ये जो लाइन हमने बनाई है विद अ फिक्स स्लोप, दिस स्लोप कुड बी स्लाइटली डिफरेंट. इट कुड बी दिस लाइन, a band of lines could actually be drawn. That's what the uncertainty in slope means, right? Everything has an uncertainty. Life is uncertain, and so is metrology, so is measurement. So the uncertainty in slope needs to be calculated, and there's a formula for that, right? So let me show you that formula, and you can revisit this as you complete your homework, which I'm going to explain in a minute on the PhysLab website. Lab 1. So if you look here, there is a under the heading uncertainties, there is a formula sheet on uncertainties. Can you turn off the lights, Faisal? फैसल लाइट जरा बंद करो. There's a formula sheet on uncertainties. सारी कर दो ना थोड़ी. 1 2 चलो. अभी देखो ये मुश्किल चीज़ें नहीं हैं, ये सिर्फ तसल्ली से करने वाली चीज़ें. एक दफ़ा ज़िंदगी, 2 दफ़ा, 1 दफ़ा ज़िंदगी में ये ज़रूर करनी चाहिए. सो दिस इज़ हाउ द एल्गोरिदम that worked in Python, the library, the polyfit function actually calculated your slope using this formula. W is the weight of each point. It's a reciprocal of the square of the uncertainty. तो ये जो एल्गोरिदम जो चला है ना पीछे बैक एंड पर, उसने इस तरीके से स्लोप कैलकुलेट किया है. ये इस लाइब्रेरी के अंदर प्रोग्राम हुआ हुआ है और उसने इस तरीके से इंटरसेप्ट कैलकुलेट किया है. दिस इज ऑलरेडी डन फॉर यू बाय द पॉलीफिट कमांड. ऑलराइट, सो यू डोंट हैव टू रीडू इट. द अनसर्टेनिटी इन स्लोप, ये जो है ना अनसर्टेनिटी इन स्लोप, u इन m, उसका ये फॉर्मूला है. The sum of the weights divided by a big denominator which has the sum of the weights, the sum of the product of the weights and the square of the x values minus the square of the sum of the weights multiplied by x values. So this needs to be programmed, this needs to be coded. You have an array for the weights, you have an array for the uncertainties, you have an array for the x's. It's just a simple matter of coding this in and you get the uncertainty in slope. So when I coded this into my notebook, this is how I do this. These 3 lines are the going into the as an input into the calculation of the uncertainty in slope. All right, so um is my uncertainty in the slope. Now r depends upon the slope. An uncertainty in slope will cause an uncertainty in resistance. Again I take the derivative of the slope with respect, I take the derivative of that formula, use the same kind of approach and find out if there is an uncertainty in the slope, how much uncertainty in the resistance would it cause. And this is how, if I have some uncertainty in the slope, I use that derivative formula and code it in. Slightly looks complicated but isn't really much complicated. You can find this out on your own. You get the uncertainty in the resistance. Okay, ये अब आपका होमवर्क है, इस काम को कंप्लीट करना. जो भी आपने नोटबुक शुरू की है इसको सेव करें और अपने आप को ईमेल करें. घर जाके 1-2 दिन के अंदर ये सबमिट करें. अपनी नोटबुक और PDF उसकी सबमिट करें. ठीक है. So once I did this uncertainty calculation, the uncertainty in slope turns out to be 67 units, 68 units. देखो 460 में ये इतनी uncertainty है and the uncertainty in resistance is 1080 ohms. So my best estimate was 14,766 ohms and the uncertainty is 1078. Right? So how will I quote my final result? ये तो मुझे आपसे पूछना चाहिए. How will I quote my final result? What is my best estimate for the resistance? Can you turn on the lights please? what should I state as my final result? जी, अनसर्टेनिटी को 1 या 2 रख लें, चलो फिर तो बोलो what should I write? What should I write? What's my best estimate for the resistance? 1 4 15,000 plus minus 1100, ठीक है, उसको मैं 2 से भी मल्टीप्लाई कर सकता हूं क्योंकि मैं 95% 2 स्टैंडर्ड अनसर्टेनिटीज तक मैं कोड कर सकता हूं 95% कॉन्फिडेंस के साथ. सो I multiply this with 2, I get about 2200. 1100 times 2 is 2200. So plus minus 2200 ohms at 95% confidence level. All right, or I can say 15.0 plus minus 2.2 kilo ohms at 95% confidence, or 15.0 plus minus 1.1 kilo ohm at 68% confidence, right? So this is how I will quote my best estimate for the resistance from all of this data. Now in summary हमने क्या किया, एक एक्सपेरिमेंट आपने परफॉर्म किया, हमने फिर आपको डेटा दिया, आपने उस डेटा को देखने के कितनी उसके अंदर गहराई है उस डेटा के अंदर, ठीक है, और एक सिस्टमैटिक प्रोसेस है उस डेटा से कोई चीज़ मेजर करना, कोई वेरिएबल, कोई पैरामीटर मेजर करना. इट्स अ हाईली सिस्टमैटिक प्रोसेस. देयर आर नो बेल्स एंड whistles, there's no hidden black magic. Everything is clear, transparent. There's a systematic process of looking at the data, organizing the data, making plots, coming up with a model that comes from your science, from your physics, then trying to match the model with the data, and from the matching process you would like to get best fit lines, preferably linear after linearization, and from the slope and intercept you can get your measurement. ठीक है, और फिर अनसर्टेनिटीज कोड करना जरूरी है. पहले देखो हमारी वैल्यू 16 किलो ओम्स आ रही थी, बट वी हैड नो क्लू ऑफ द अनसर्टेनिटीज. नाउ वी गेट समथिंग अराउंड 15 kilo ohm and we now have some level of confidence in this result. Now the homework is, before I tell you the homework, are there any questions? Any questions? कोई और पूछना चाह रहे हैं आप कोई बात? अगले 2 सेशंस में भी हम आपको गाइडेड इंक्वायरी करवाएंगे, एक्सपेरिमेंट्स करवाएंगे गाइडेड अंदाज में, ताकि आपको ये चीज़ समझ आ सके, ठीक है. नाउ व्हाट आई वुड लाइक यू टू डू, go home, save your data, save your notebook file, complete it, do all the working in your notebook file, and send us a PDF copy as well as a notebook file, both of them together to your TAs, to your lab instructors. PDF and your Jupyter notebook file, your IP and YB files.
Sir, our homework is to do the same thing in job.
And you need to kind of complete the argument that we started today and also do a log version, a different kind of linearization. ठीक है, चलें जी, थैंक यू, इंशाल्लाह.